This is the weir at Kepezkaya as viewed from the downstream side. Now we are approaching the weir from the upstream side in this three-dimensional model. On the left you can see the intake channel, and on the right side you can see the bypass channel. The intake channel is comprised of 4 separate bays, each of which contains a trash rack, which are installed to prevent debris from reaching the turbines. At the end of the intake channel is the intake gate and the tunnel entrance. Now as we swing around here, on the right side we can see the overflow structure, and straight ahead we can see the 2 radial gates, which control the water flow through the bypass channel. Now as we fly overhead again, we can see the 4 separate bays that make up the trash rack structures. And then we can see the singular trash rack machine sitting on top. The problem we are addressing here is accumulation of sedimentation and debris against the trash racks as illustrated here. Several times during the year, the levels of debris and sedimentation against the trash racks become high enough to block water from entering the intake channel. Now when this happens, the water level on the tunnel side of this structure starts to drop, and we can see that occurring here. When this water level drops, it means there's less water coming into the tunnel, and therefore there's less energy production at the plant. Now we're going to take a look at the trash rack machine we have in place. This is the technology we have currently installed. It's a typical wire rope type of trash rack maintenance machine. Now here we can see the sled portion as it's lowered down the face of the trash rack to the bottom. Once it's at the bottom, the tines turn 90 degrees and then pick up material as the sled is pulled back up. Once it's at the surface, the material is removed by hand. Now the next picture will illustrate how bad the conditions can become at Kepezkaya. Unfortunately, our machine is not built for the size and volume of this type of debris. It's just simply been ineffective. It's really built for smaller, lighter material like leaves. As a result, the trash racks become blocked as we see here, and then that water level differential becomes very significant as shown here. So here's our current response. When the water level on the tunnel side of that intake channel reaches a predetermined point, where we've determined the generation losses are unacceptable, the decision is made to schedule an outage to go in and maintain the trash racks. So the radial gates are open as we see here, and then the weir basin is emptied. Once the conditions are safe, a working machine actually drives down through the riverbed to reach the front of the trash racks. Now here are a few pictures of the machines in action, and you can see them actually driving right up the middle of the riverbed. Now this solution works very well when we actually have access. The problem is that there are times where we cannot lower the water levels. There's simply too much water coming through this river valley, and we cannot lower the water levels to a safe enough level. So you can see here from this example, we're opening the radial gates, but the water level's simply too high on the downstream side, and then the upstream side we cannot lower it. And so when this happens, we have no choice but to basically wait out the floodwaters. But this can take 5 or 6 days. Now here are 2 other parameters we need to consider. The first is that opening on the top of the surface, and you can see it's extremely narrow. And the second is this vertical debris wall, which prevents us accessing it from the bridge. Now here's the solution we're proposing.
Remove the existing trash rack cleaning machine, modify the existing concrete structure, build a new concrete work platform, and finally install a new working machine. Now we will walk through the design and the execution plan required to reach this final design. The first step is to install a new steel debris wall. This will serve the same function as the existing concrete debris wall that will be removed. The existing trash rack cleaning machine will be removed along with portions of the concrete structure, which include the horizontal decking followed by the vertical concrete debris wall sections. The demolition methodology will use diamond wire cutting technology, and the decking and debris wall will be removed in slices, similar to what's illustrated in these pictures. This technology provides very precise cuts, which minimizes damage to the remaining structure. Now here's a section view of those steps. We have a new steel debris wall, remove the trash rack machine, remove the deck sections, and then finally remove the vertical concrete debris wall. Next, we'll illustrate the new concrete working platform. The first step is to install concrete I-beams. These are identical to those found in the existing bridgeway that you can see in the background. This is followed by the installation of these vertical steel components of the guide system. These are going to be embedded in the first pour of the concrete deck. Once the concrete is set, the tread track guides will be installed. These track guides will maintain the travel alignment of the working machine. Then there will be another concrete pour, followed by the installation of the steel guide rails. At this point, 2 of the 3 components of our guidance system will be in place. We have the tread track guides and the guide rail assembly. After the concrete barrier is completed, we are ready for our working machine. Now this working machine is a standard 35-ton excavator with a few aftermarket modifications, such as a sliding cab extension, which increases visibility for the operator. We'll now swing around and get a closer look at the roller guide assembly. There's a roller guide assembly installed on both sides of the chassis. They're mounted directly to the track frame. These rollers are to be in contact with the guide rail assembly in 2 different angles. The roller guide assembly and the rail guide assembly, along with the tread track guides in the bottom, they prevent the working machine from vertical movement and from horizontal movement off of the travel path. The telescopic arm is very powerful, and these systems minimize the risk of the machine tipping over. These systems also maintain the alignment of the machine, minimizing the risk of the operator driving towards the edge. So not only does the design increase the safety, but it also increases the efficiency of the operations. Now we will take a closer look at the operations of the working machine. The arm is a marine-grade telescopic arm. It's attached to a standard boom. It's a 2-piece, entirely hydraulic arm, which increases the power, speed, and durability of the component. The lower teeth of this grab shovel act to pry material off of the face of the trash rack, as well as penetrate into the thick debris. The upper teeth secure the shovel load as we move the shovel back up to the top. On the surface, the arm is pivoted to this horizontal position, and the shovel is then positioned over the dump truck. A hydraulic mechanism then pushes the shovel load into the dump truck. The working machine then returns to its original position, having completed 1 cycle of its operation. Now this design is a much more powerful and effective solution over conventional trash rack machines that are available on the market. Here again is the current design, and then we can see our proposed design. The use of a standard type of excavator provides a very good solution in terms of power and capabilities for about half of the installation costs of other custom trash rack machines. It's important to note that this machine can still be used as a normal excavator for a wide range of other tasks. It's not confined to this location. And the cost and response time for maintenance and repairs for a standard type of excavator are much easier and much more cost effective. Now with this design, the excavator will be able to maintain the trash racks under any condition from this working platform. As we mentioned earlier, there have been occasions where we have lost all generation revenue for 5 or 6 days during high water conditions. With this design, we will never have to empty the weir for maintenance, and we will avoid those losses entirely. This will save hundreds of thousands of dollars of lost revenue each year, which will result in an annual revenue gain of about 6%, which over the long term will equate to tens of millions of dollars for the project. This concludes our presentation. Thank you for your time.